Welcome to lecture 13th of module 3 of course called Game Theory and Economics. So, what we have been discussing so far is that we have been discussing various aspects of auction through the model of game theory, and the two kinds of auctions that we have discussed are second price sealed bid auction and first price sealed bid auction. So, today what I propose to do is to look at other sorts of auctions which are prevalent, and then end this topic today itself. So, one kind of auction which is neither second bid, second price or first price is what is known as all pay auction. In all pay auction, the person who is not getting the object also pays, which means that suppose I have bid BI, but BI is less than the highest bid. Suppose this is BH. In that case, I do not get the object, but nevertheless I have to pay this BI. So, this is a little bit tough on the people who are not getting the object, but this kind of auctions are there. For example, it may happen that if we can think of any real life example of this kind of auction, all pay auction, you can think of various political lobbies which are trying to influence the functioning of the government, various business lobbies for example. Now, when these business lobbies try to influence the functioning of the government, the decision of the government, maybe they pay bribes to the ministers or bureaucrats. Now, it may happen that I pay bribes, but the decision of the government does not go in my favor. So, in that case I pay something which is BI, which is like a bid for the decision to go in my favor, but at the end of the day, if the decision of the government does not go in my favor, it is not that I get back this money which I have already paid to the various functionaries of the government. So, there are some real life examples, examples of this all pay auction. Now, if we apply, interestingly, if we apply this all pay auction in case of the setting of suppose second price auction, then what happens? Suppose this also has this all pay provision. Then what happens is that this second price auction becomes similar to the war of attrition game that we have seen before, except for some few cases. Why I am saying this is that in second price auction, if we have this all pay provision, then what is the payoff of any individual? It is VI minus BI if BI is greater than B bar. Remember, B bar is the highest bid of the other players, or BI is equal to B bar and I is less than J, where J is equal to B bar. So, it may also happen that I bid the highest bid of the other players, but my index which is I is less, and therefore, I get the object, and in that case my payoff is this much, V I minus B I. And it may happen that I do not get the object, in that case I get 0. This happens if B I is less than B bar, that is my bid is less than the highest bid of other players, or my bid is same as the highest bid of the other players, but my index is more than the indexes of these players who are bidding the highest. In that case also my payoff is 0. Now, look, this payoff structure is same as the war of attrition payoff structure, except for B I is equal to T I. Because what was happening in that case is that, oh sorry, this is equal to minus P I, because when I am not getting the object I am still paying. So, this was the difference which was not there in case of second price auction, but right now we have this case of this thing, and this should be B bar. Okay. So, this is the case where I have only 2 players. If I have only 2 players, payoff function of each player is equal to V I, the valuation of his valuation, minus B bar is the second highest, if I get the object, and even if I do not get the object but my index is lower, then my payoff is this much. If I do not get the object, then whatever time I have spent in waiting for the object, whatever time I spent in case of war of attrition, but here in case of second price auction, whatever bid I have made, which is given by B I, that is my loss from this whole exercise, because I am not getting the object. So, this is the case, and what is important is that this is exactly like the war of attrition game, where if I get the object, then my payoff becomes V I minus T j. Here T j is equal to B bar. B bar is the bid of the other player. And if I do not get the object, that is I give up earlier than my rival in case of war of attrition, I lose the entire time that I spent, the value of that time. Here it is minus P I, there it was minus T I. Except the difference is that in case of tie, in case of war of attrition, people were getting minus half of V I minus T I. So, that was the case in case of tie, but here we have the object going to the person who values the object more. So, tie breaking rule is different here, but besides that, this game is same as the game of war of attrition. Now, so this is one interesting thing, and the second interesting thing is that if I apply this idea of all pay in case of first price auction, then what is the equilibrium that emerges from here? And the answer is that if I have a first price auction where people have to pay irrespective of the fact that they get the object or not, then there is no equilibrium. No Nash equilibrium. And what is the proof? Proof is the following. Suppose there is a Nash equilibrium. Nash equilibrium. Now, let the bits be different in the equilibrium. If there are equilibria, then they can be of two types, either in the equilibrium the bits are different, or in the equilibrium the bits are the same. Let us take the first case, that the bits are different. Now, so I have B1, B2, where suppose without loss of generality B1 is greater than B2. Now, this a Nash equilibrium? This cannot be a Nash equilibrium. Because player 1 who is bidding more will deviate and bid something less. If he bids something less, he can improve his payoff. So, because 1 has a profitable deviation, if he bids less than B1 but more than B2. So, this cannot be a Nash equilibrium, because at least one person is having a profitable deviation. What can be the other possibility? The other possibility is that the bids are the same. And suppose the bits are B. Can this be a Nash equilibrium? Here I have two possible cases. One is that B is greater than 0 or B is equal to 0. Now, if B is greater than 0, then who is the person who is getting the object? One is getting the object, but is this a Nash equilibrium? This is not a Nash equilibrium, because 2 has a profitable deviation. The reason being, here at BB he is paying, this player 2 is paying B, which means his payoff is minus B. So, this is absurd for him to go on paying this B while not getting the object at all. So, he can at least bid less than B, and that is a profitable deviation for him. So, this is not a Nash equilibrium. The last case that is left is this a Nash equilibrium, that BB and the value of B is equal to 0. Here notice, though player 1 is getting the object, the difference between the previous case is that player 2 cannot bid less than this. So, the previous argument cannot be applied in this case, but here player 2, in this case player 2 can bid more than B and get the object, and that is going to be profitable, because if you remember, one assumption that we had taken before at the start is all the valuations are positive. So, whatever be the valuation of player 2, it might be very little, but as long as this player 2 bids more than 0, he can make a positive payoff. Right now he is making a 0 payoff. So, from here also player 2 has a profitable deviation. So, this is not a Nash equilibrium. So, basically we have exhausted all possibilities, and so we have not found any Nash equilibrium in case of first price auction, where everybody is paying his or her bid. So, this was the case of all pay auction. Now, we also have another kind of auction which is known as multi-unit auction. Here the auctioneer is auctioning not a single good, but different units of a good. So, it may happen that the auctioneer has k units of a good, which this k units the auctioneer likes to auction off, and there are bidders. Now, since there are k units of a good to be auctioned off, a bidder, when he submits his bid, is not going to quote just one price, but a vector of prices having k elements. So, maybe B1 will look like this: B11, B12, B1k. Similarly, the last person so in this way everybody is going to submit bids, and for any unit the highest bid will be picked up, and that person who is submitting the highest bid is going to get that unit. So, that is very clear. However, it may happen that the price that this person is paying to the auctioneer varies according to different rules of the game. So, we are going to discuss only two rules of the game. One is what is known as discriminatory auction, and the other is what is known as uniform price auction. Basically, in discriminatory action, what the price the players are paying for the units that they are getting, this model is trying to imitate the model of first price auction. So, for any unit, the person who is getting the unit is going to pay the price which he himself is quoting. So, it is like the first price auction, just we are taking many units. In case of uniform price auction, what we are trying to imitate is the second price auction. So, which is the price that that these people are paying to the auctioneer? The price that is being paid is the highest among the rejected bids. To elaborate what the idea is, for each unit there is one price which is winning the auction, and there are many prices which did not win that unit, and there is a highest among those prices. So, this is the highest rejected bid for that unit. Now, if we compare all the highest rejected bids of all units, there will be one price which will be the highest among these highests. So, that is what we mean by the highest among the rejected bids, and this highest rejected bid is the price that all the people who are getting the object are going to pay. So, the price that the winners are paying in this case is the same, it is uniform, that is why it is called uniform price auction. And you can see that it is like the second price auction in the sense that the price is not the bid that I submitted, but it is a price which has been rejected. But there is a complication here. It may happen that the price that I am paying is more than what I bid for. For example, take this case, this is unit 1 and this is unit 2. In unit 1, player 1 has submitted B11, player 2 has submitted B21. In unit 2, player 2 has submitted a higher bid, bid 2, it is B22, and player 1 has submitted B12. Now, here the highest among the rejected bid is this much, but this bid is higher than the bid that player 2 submitted for this second unit. So, there is this added complication. What we are going to do is to look at one exercise from multi-unit auction. Here is the exercise. 200 people are willing to wait in line to see a movie at a theatre whose capacity is 100. Denote person I's valuation of the movie in excess of the price of admission expressed in terms of the amount of time she is willing to wait by Vi. That is, person I's payoff if she waits for Ti units of time is Vi minus Ti. Each person attaches no value to a second ticket and cannot buy tickets for other people. Assume that V1 is greater than V2 etc., greater than V200. Each person chooses an arrival time. If several people arrive at the same time, then their order in the line is determined by their index. If a person arrives to find 100 or more people already in line, her payoff is 0. Model the situation as a variant of discriminatory multi-unit auction in which each person submits a bid for only one unit and find its Nash equilibrium. Arrival times for people at movies do not in general seem to conform with the Nash equilibrium. What feature missing from this model could explain the pattern of arrivals? So, to translate this story into simple English, there are 200 people, they want to watch a movie, but in that movie theatre the capacity is for 100 people. So, this is capacity for 100 people. And the tickets are going to be distributed at a particular point of time. Now, if I come early, then I have a better chance of getting a ticket, and it may happen that I am the first person to arrive at the ticket counter. So, I will be in the first in the line. So, I will definitely get the ticket. But if there are more than 100 people already in the line and I arrive there, then I will not get the ticket and I will not be able to watch that movie. In that case, my payoff will be 0. And how much people value watching the movie that varies from person to person. So, this is what is being assumed. The indexes are such that the first person values the movie the most, the second person the second highest, etc., etc. And how do I write the payoff then? Payoff is written as Vi minus Ti. There is this valuation from the movie which I get Vi, but I had to stand in the line for some time to get the ticket. So, that is denoted by Ti, and both these are expressed in the unit of time. So, I do not have any problem of unit. I can subtract Ti from Vi because they both of them are in time in terms of time. So, in this setting I have to find out what is the Nash equilibrium action. Remember, what is happening is that every person is choosing a t. T is the waiting time. So, larger is t, the less well off you are, because this Ti is going up. So, u is going to go down. At the same time, if I choose a small t, I will not be able to watch the movie because there will be more people already in the line. So, that is the thing. And why am I calling it a multi-unit auction? This is a multi-unit auction because there are 100 units, in the sense that 100 is the capacity. These 100 units are sold off and each person is submitting the bid for only one unit. So, he or she is bidding for only one unit and the price that they are paying is in terms of T. Greater is the T, less well off they are. So, this is how it can be seen as a kind of auction. Now, we have to find the equilibrium of this game. So, that is more or less it. To close it, to close this chapter on auction, just one more thing that I wanted to discuss is the following, is the case of lobbying. Lobbying can also be seen as auction. What I mean by lobbying is the following. Suppose there are different social groups, maybe business groups, they are wanting the government to follow a particular policy, the policy which is most beneficial for them, and there might be divergences. I might like policy X to be followed, my rival group might be wanting the government to follow some other policy, maybe Y or Z. In that case, we shall try to influence the government, and it may happen that the government is in a way is selling these policies to people. Whoever is bidding the highest, which party is bidding the highest, that party is getting his or her policy of choice to be implemented by the government. In that case, can we apply the models of Nash equilibrium or model of auctions that we have discussed so far? Let us take the following game. Suppose there are two lobbies, lobby A and lobby B, and there are three policies that can be taken by the government, and the numbers here indicate the benefits that the lobbies are going to get from the policies. So, in short, if X is the government's policy, neither A nor B get anything from this policy. If Y is implemented, then lobby A gets 3 payoff from the policy, lobby B gets minus 100 from the policy. So, it is very bad for lobby B, but little good for lobby A. The opposite thing happens if Z is implemented. B is getting 3 and A is getting minus 100. Now, what is the rule of the game? What rule government is telling to this lobbies to follow? And suppose the rule is the first price auction. Which means that each lobby will tell the government how much money it is ready to pay to the government to get its favorite policy implemented. So, if lobby A quotes a higher bid, then lobby A is going to implement his policy, and in that case lobby B is not going to pay anything to the government because its policy is not going to get implemented. So, that is the setting. Now, the claim is the following. Claim is that A will bid 103 for Y, B will bid 103 for Z, and that is a Nash equilibrium. Okay, so let us do one exercise on this idea of multi-unit auction. This exercise is called internet pricing. I shall write down the question first and then we shall solve this problem. So, this is the question. Let me read the question. A proposal to deal with congestion on electronic message pathways is that each message should include a field stating an amount of money the sender is willing to pay for the message to be sent. Suppose during some time interval each of n people wants to send one message and the capacity of pathway is k messages, where k is strictly less than n. The k messages whose bits are the highest are the ones sent, and each of the persons sending these messages pays a price equal to the k plus 1th highest bit. Model this situation as a multi-unit auction. Use the same tie breaking as the one discussed before. Does a person's action of bidding the value of her message weakly dominates all other actions? So, this is like the following multi-unit auction. Okay, so players, who are the players? N bidders. Okay, each wants 1 unit of the k units available. Okay, and they have their valuations also. So, V1, V2 etc., Vn are greater than 0 are their valuations. Actions. Actions are nothing but bids B1, B2, Bn, and finally preferences. Payoff is maximized. Okay. Payoff of player I, let us call it Ui, is equal to Vi minus B bar. If I gets 1 unit of the k units, all right, and this will happen if i's bid is not rejected, B bar is the highest rejected bid. So, in this case B I is greater than B bar. It can be equal to B bar also, or B I is equal to B bar, but I is greater than index of the person whose bid is B bar and is denied. So, this is the case when I is getting the object, or 0 if I is not getting the object. So, in this case his bid is being denied. So, this is how it can be seen as a auction game. Now, second part of the question is the following. Does a person's action of bidding the value of her message weakly dominates all other actions? So, take the player I. For player I, BI is her bid and VI is her valuation. Now, let P bar is the highest rejected bid. Now, for let us say VI greater than B bar, okay. If BI is greater than B bar, I's payoff remains at VI minus B bar. This is what he gets. If BI is equal to B bar, but I's index is less than the player who bid B bar, then also I's payoff is equal to minus B bar. If BI is less than B bar, I's payoff is equal to 0, right. Now, he is not getting the object. And what could be the other possibility? That BI is equal to VI and this is greater than obviously B bar. In this case, payoff is equal to VI minus B bar, and if BI is greater than VI, payoff is equal to same as VI minus B bar. So, by looking at all these different possibilities of BI, we are taking different values of BI, we are seeing that whatever be the value of BI, if it is not equal to VI, then payoff of I cannot be more than what he is getting by bidding just equal to VI, which means that in this case, so if VI is greater than B bar, bidding BI not equal to VI gives I at most VI minus B bar, which he is getting by bidding BI is equal to VI. All right. So, BI is equal to VI weakly dominates other actions. Similarly, we can show VI weakly dominates Vi is less than B bar or equal to B bar. So, this is the proof that if in this case of multi-unit auction, where a person who is getting the object pays the k plus 1th highest bid, the valuation of one's valuation of the object weakly dominates over all her other actions. So, this was more or less our discussion of auction theory. What we are going to do in the next lecture, I am going to introduce the topic right now. Is known as accident law. So, law and economics is basically is a subdiscipline within economics, where what is tried to be analyzed are the effectivity of laws, whether these laws are in line with the economic principles such as efficiency, productivity, etc., etc. And can we have certain laws, therefore, can we have certain laws which are efficient in the economic sense, or can the laws be improved? So, here also we are going to look into a particular sort of law which is known as accident law. So, in an accident law, what is the general setting? There are two parties of this accident law. One is, suppose, the injurer, so this is player 1, who will be called the injurer, and there is this player 2, who is the injured person, let us call him the victim. So, to visualize this thing, there can be several examples. What one example could be that a pedestrian is crossing the road and suddenly a car comes and hits him. The loss that occurs from this accident only is accruing to the victim, that is why he is called a victim. The car owner or the driver is not at a loss now, he is not getting harmed in any way. But now the question is, when this accident is taking place, there are two sides to the story. It might happen that the injurer was careful in driving, whereas the victim was careless, he just went into the street without looking at other different directions, and that is why the this loss and this accident happened. Or it could be the other way, that the victim was very careful in crossing the street, but the injurer, the car driver, was rash, and that is why it happened, this accident happened. So, can there be a law which apportions, which assigns a kind of care that these two parties should take, such that this kind of negligence from each side is minimized, and we get outcome which is efficient for the two parties taken together. So, this is something which we are going to look into in the next lecture. So, before we finish, what we have done in this lecture is that we have discussed the various aspects of auction theory. We have gone beyond first price auction and second price auction, and we have started discussing what is known as accident laws. Thank you. In first price all pay auction proved that there is no Nash equilibrium. Now, remember, in first price all pay auction, how is it characterized? Everyone pays equal to her bid, and the highest bidder gets the object. Now, here we have to show that there is no Nash equilibrium. How? Let us say B1, B2. We are talking about two players. Okay. Suppose there are two players and their bits are B1 and B2. Can there be a Nash equilibrium? Suppose the bits are such that B1 is not equal to B2. So, this is case 1, and there could be a case 2 where B1 is equal to B2. And suppose when B1 is not equal to B2, let B2 is greater than B1. Now, in this case, obviously player 2 will get the object. And pay B2, but which means that there is a profitable deviation for player 2. She can bid less than B2 and still win the object. So, this thing B2 greater than B1 cannot be a Nash equilibrium. So, this case is then ruled out. If the bits are different, then they cannot be Nash equilibrium. If bits are equal, then is there a profitable deviation for one player? Here again we shall see that 2 has profitable deviation. This is because in the case where B1 is equal to B2, one is getting the object and 2 is paying B2 without getting the object. So, 2 can bid B2 greater than B1 and get the object. In which case her payoff rises. So, we find that none of these two cases, first when B1 is equal to B2 or B1 is not equal to B2, in none of the cases there is an equilibrium. Hence, here no equilibrium exists. Question number 2. So, in question number 2 we are given a matrix where the numbers are showing the benefits that these two parties A and B get from each of these three policies X, Y and Z, and we have to show that in a menu auction the equilibrium exists with the following bits: 51.5, 103.0 for A, and for B 51.50, 103. Now, here so these are the bits that are we have to prove that they are the equilibrium bids. Now, why they are equilibrium? Because if A bids less in X, then Y gets implemented. And in which case her payoff is even less, whereas now what player 1 is getting is he is paying 51.1.5 and getting 0, which means he is getting minus 51.5, whereas if Y gets implemented, he will get minus 100. So, bidding less for X is unprofitable. Similarly, we can show that bidding less for Y is also unprofitable. Okay. If both X and Y are bid less by A, then Z gets implemented, which means that in that case A will get minus 103 as the payoff. So, deviation by A is unprofitable. Similarly, we can show that deviation B is also unprofitable. So, that is it.